Okay, you guys, we made it to our last lecture for this unit. Very exciting. The last thing I want to talk to you guys about involves the energy of reactions, whether or not a reaction is absorbing energy or releasing energy. This is really important for us as chemists because it helps us decide what we can do with that reaction. Like, are we trying to make a hot pack or a cold pack? Can we use the heat that is being produced by a reaction to do work? So this is all, very, very important stuff. And we'll definitely take closer looks at this next year in AP Chem. But for now, we're going to talk specifically about heat. So when you hear the word energy, sometimes we don't really think about what is energy? Energy, technically, is the ability to transfer heat, variable for that is Q, and do work. Now, when you think about work, typically you think about that in terms of physics, like, a car driving down a street is doing work, or somebody throwing a ball is doing work. In terms of chemistry, when we have expansion of gases in chemical reactions that expand in volume and take up space, that's what we consider to be chemical work. It's what we call pressure volume work. Again, we're going to talk about this in a lot more detail next year. But for this conversation, I want you guys to focus on thermal energy or heat of reactions. That's what we're going to look at today. Do these reactions produce heat or absorb heat as they take place? Now, one of the other important factors that you guys need to understand is what it takes for a reaction to occur. And what it takes for a reaction to occur is a collision between reactant molecules. They have to hit each other in order to break the bonds of the reactants and create the bonds of the products. Now, this collision has to have two key factors. We call these effective collisions. The collision has to have the correct orientation. In other words, if we want to create a bond between substance A and substance C, substance A and substance C have to hit each other. Like A hitting B is not going to create the reaction that we want or the bond that we want to form between A and C. So these molecules have to hit each other with the correct orientation in order to form the new bonds of the products. And they have to collide with enough energy to break those bonds of the products and break the bonds of the reactants and then form the bonds of the products. This process is, and this process of breaking and forming of bonds is what we call going through a transition state and overcoming what we call the activation energy. So the collision needs to have enough energy to overcome the, to overcome the E sub A. This is our activation energy. We'll define this further here in a little bit. Okay, so be thinking about that as we look at the following potential energy diagram. As we look at this diagram is showing us on our y-axis potential energy of position that the molecules have, and progress of the reaction on our x-axis, or you could consider that to be time. So we can see here that substances A and B, our reactants, so A plus B, are making substances C and D. These are my reactants, and these are my products. In order for these reactants to turn into these products, like we said, there have to be collisions, and those collisions have to have enough energy to get up over this energy barrier. The amount of energy needed to get those reactants, so this is how much energy my reactants have, up over this energy barrier, this distance from here to here, is my activation energy. So in this case, for this reaction, it has an activation energy equal to 100 kilojoules minus 40 kilojoules. So my activation energy in this case is 60 kilojoules. This is, the top of this peak is where the collision occurs. This is what we call the transition state. This is where the collision of the reactant molecules occurs, where those reactant bonds break, and where the product bonds begin to form. Then, obviously, this reaction wouldn't happen if it didn't lead to a reduction off of that transition state or a more stable state. So the peak always goes up and then starts to come down. Now, how far down it comes depends on the reaction, but you're always going to get this characteristic shape of the peak going up, some energy needed to be added in order to get up over that transition state, and then energy released on the way down as those product bonds form. Now, the difference between how much energy the products have versus how much energy the reactants have is going to help us determine whether or not this reaction was endothermic or exothermic. But I'm getting a little ahead of myself. Let's first define some of these variables that I have shown you here on the diagram. Activation energy. The energy needed for the reactants to pass through the transition state. For this collision to occur, and thus the breaking and forming of bonds. The transition state is the peak of the graph, where the reactants have the most energy, where they collide and begin to turn into products. Okay, so this is how much energy my reactants have. This is how much energy my products have. The amount of energy it took to get my reactants up over that energy barrier into the transition state is my activation energy. And in this case, 60 kilojoules. Now let's take a look on the last page as to what it looks like when a reaction is endothermic versus exothermic. This is what we call the heat of reaction. Now you'll notice I changed variables on you, okay? I was talking about heat as Q. Now, technically, Q and delta H are not the same thing. However, for our purposes, we can say that they're the same thing. Q is equal to delta H when we have constant pressure conditions. So Q at constant pressure is the same thing as delta H. And delta H just stands for the heat transferred in a reaction. We'll talk more in AP Chem about why this constant pressure situation is important. Okay. So let's look at two different potential energy diagrams here. If we are looking at diagram A, we see a scenario where the products ended up with more energy than the reactants. Now again, we see this standard shape, right? Like we see that the reactants needed to gain a certain amount of energy, sorry, that was a really not straight line, to get up over that activation energy barrier. And then the energy started to go back down, but it didn't go all the way back down to how much energy the reactants had. In fact, the products are ending up with the energy of your products, is ending up greater than your energy of your reactants. Well, how is that the case? The case to make for that, or that happens when a reaction absorbs energy. And we call reactions that absorb energy endothermic reactions. And the sign for our delta H for endothermic reactions will always be positive. Because when we do our delta, when we calculate our delta H, it's always delta H final minus delta H initial. So the delta H for a reaction is always equal to the heat or the energy that the products have minus the heat or the energy that the reactants have. So here, if we do products, which is a bigger value, minus your reactants, which is a smaller value, we're going to get a positive delta H. So this is an example of an endothermic reaction. Energy was absorbed, positive delta H. Now I'm writing this in blue because endothermic reactions to us in the surroundings feel cold. They feel cold because they are absorbing heat. Well, where are they absorbing that heat from? From the surroundings, like our hand or the water bath that the reaction is taking place in. So let's summarize endothermic reactions this way. Endothermic reactions absorb heat. The products end up with more energy than the reactants. And lastly, the surroundings get colder, as the surroundings are providing the heat that is being absorbed by the reaction. Let's take a look at what happens if the situation was reversed. Here we have a situation where our reactants have so much energy and they are going to go up over this activation energy barrier through the transition state and begin to release energy to make the products. In this case, the energy of the products is less than the energy of the reactants. We end up with less energy than we started with. Well, how did that happen? How do we end up with less energy than we had at the beginning? Through a release of energy. This is what we call an exothermic reaction. If we subtracted the products minus the reactants, again, that's how we get our deltas, final minus initial, we're going to get a negative delta H. Oops, I forgot with my endothermic to remind ourselves of positive delta H. Okay, so exothermic reactions release heat. Products end up with less energy. Than the reactants. If that energy was being released by the reaction to the surroundings are gaining energy. And thus, they get hot. They feel hot. We have a negative delta H. If you want to imagine, system versus surroundings, this can be tough for some people. Like imagine that the reaction is taking place inside this box. Like here's my reaction taking place. If this reaction is endothermic, that means energy needs to go into the box, right? The heat needs to go that way, into the box. There's my heat going from my surroundings into the system. So the surroundings is losing energy as the reaction is gaining energy. I realize you can't see that arrow very well at all. So like this. That's the direction my heat is traveling, from my surroundings into my system. So my surroundings is going to get cold because it's losing the heat. If I'm talking about an exothermic reaction, again, the reaction is taking place inside the box. If the reaction is losing heat, the heat is going out from the surroundings out into the system. So the system is gaining the heat and thus gets warmer. The last thing I want to talk to you guys about are catalysts, because we've talked about catalysts. We know that catalysts speed up reactions. But how do they speed up reactions? Like I've been telling you that catalysts are not reactants, they're not products, they don't show up in our reaction except over the top of the arrow. What is it that catalysts are doing to, in fact, speed up the reactions? What they do, they speed up the reactions by lowering the activation energy. Now, there's different ways for that to happen. Oftentimes, what a catalyst does is it bonds to one of the reactants, blocking off a portion of that reactant molecule for a collision, so that you're more likely to get a collision in the place that you want to get a collision. So, in effect, the catalyst can mess with the orientation of the molecules to make sure that we get more collisions happening with the proper orientation. Think about them as like enzymes that make biological reactions happen faster by blocking off certain bonding sites. So, what would a catalyzed pathway look like in our potential energy diagram right here? It's kind of fun. We get to draw a new lower activation energy hump. A catalyzed reaction would have a lower activation energy. So instead of our activation energy going all the way up to that top peak, now my activation energy is lower. So this is what we would call the catalyzed. Why do I feel like I want to put a Z there? That looks wrong. Should it be a Z? No, because catalysis is that. I'm going to stick with the S, and maybe I should just stop and Google it in the middle of my video, just to annoy you guys. Google, tell me, how do I spell? No, I don't want to go to my drive. I just want to go to regular Google. Catalyzed. Yeah, the S is right. I don't know why it looks so gross to me. I really feel like I want to change it to a Z, but I'm glad I didn't, because that is correct. Okay, are you sick of me yet? Did you stop the video? You could have, because that's all we had to do. We are done. Get ready for next week, you guys. We get to start quantifying this stuff. Yay, dimensional analysis. Get some fresh batteries in your calculators. See you then.